In this video, we're going to be talking about electric fields and field mapping. So, an electric field map with its equipotential lines works the same way as a topographical map. On the bottom, we have a three-dimensional representation of a geographic feature. Two hills with a valley in between. On the top, we have a topographical map. And what we see on the top as concentric rings corresponds to areas of equal altitude on the hills, where we separate the lines on the map by regular intervals, like every 100 feet. On an electric map, I'd separate them by different voltage levels. Separate them by 5 volts or 10 volts or whatever is appropriate. Also on the topographical, or on the bottom map, we see these lines coming down the side. Those lines show the direction of the flow of water off of the surface as gravity pulls water to areas with lower potential energy. We have a similar feature with our electric field lines, where positive charges are pushed away because of the Coulomb force from areas that have positive charge. And so when we draw these electric field lines, it shows the direction, if this was a field map, the direction that positive charges would flow off of or away from fixed charges on the field. Electric field lines never cross, because just like two water flows do not cross each other, they change direction and are influenced by each other. In the same way, electric field lines never cross. And our electric field lines are always perpendicular to the equipotential lines. They always cross perpendicular. And where those equipotential lines are close together, like on this top map, that means that's a steep area. Where they're farther apart, that means that it's a relatively flat surface. So if we take this concept into a simple electric field map, if I want to map the region around a positive charge, I want to think about a positive test charge. Our test charge is always positive. If I put a positive test charge on the map, it would be pushed away from the positive charge. Regardless of where I put it down, it's going to be pushed away. Okay. And that corresponds to a visualization of a high potential energy peak in a three-dimensional vision, with the electric field lines pushing out and away. And in areas where there are a lot of electric field lines close together, that's where you have a very steep potential energy. If you go farther out, you'll notice that the field lines are further apart from one another, and that's a flatter area that has less electrical force pushing things away from each other. If we draw the equipotential lines, those form concentric rings around the positive charge in the same way that they would form rings around the central point. If we do the same thing with a negative charge, we're envisioning a pit or a valley. If I put a test charge down near a negative, it's going to flow down and into the hole. So the shape, the general shape of the field looks very much the same, except the arrows point in the opposite direction. Because my surface is essentially flipped it upside down. And my equipotential lines, again, are concentric circles, sort of. If we look at two charges on the same map, like a plus and a minus, a test charge that's put down near the positive is going to be pushed away from the positive at the beginning because the negative charge is far away and doesn't have as much influence. The closer I get to the negative, the more I get pulled around and inward into the hole. If I start out on a trajectory that's farther out, I'm going to go farther away before I get pulled in. And if I'm going more outward, then the main influence is the thing that I'm close to. Now you'll note that there's symmetry here in that across the axis, the top side of the picture looks just like the bottom side of the picture. And you'll also notice that I've got one plus and one minus, and I have the same number of arrows coming out of the positive. There's 6 arrows coming out of the positive here, and there's 6 arrows going into the negative there. That happens because they have the same amount of charge. If they had different amounts of charge, I would have to have the same ratio as the ratio of charges. So twice as much charge would have twice as many arrows. If I look at that same surface in a three-dimensional view, I would have a hill and I would have a valley that would be roughly the same size. And I would have flow that would come out and around to go in. That's not working really well at all. Never mind. I'm going to limit my charge lines on that map because that's not working for me today. All right. If I take the same picture and I go to 2 positives versus 1 negative, my electric field lines would go farther out from the 2 positives before they start getting reeled in toward the negative, because the positive having more charge would have a longer reach. And I kind of have to go around the other side before I really curl in toward the valley, because I'm coming down off the mountain so fast I kind of overshoot and then come back around and in. Now I want to honor the fact that I've got twice as much positive, and so I can do that by adding more arrows to the two positives. Since I have 4 going into the negative charge, I should have 8 coming out of the positive charge, because an 8 to 4 ratio is the same as a 2 to 1 ratio between the charges. And a doubly high peak, which would go into a shorter valley, is more like what I'm talking about. And if I'm talking about electric field lines, this doubly high positive is going to have more rings than the singly low negative. And so I would only draw 1 ring around the negative, and I would draw 2 rings around the positive to maintain that 2 to 1 ratio. Okay. If we talked about one other one I want to put up, a plus and a plus map, the flow between pluses is repulsive from both charges, and so what you end up with is what they call a saddle point, where charges released aimed toward the middle are going to get channeled out the sides. And if we had multiple charges on this one, that middle point, that balanced in the middle point, would move closer to the smaller amount of charge. Okay, so let's talk about calculations with electric field strength. Electric field strength is related to the force, but it is the force per unit charge. It is in newtons per meter. Per coulomb. Newtons per coulomb. And so if I want to figure out how much force there is at a particular place on an electric field line, I take the electric field line and I multiply it by the amount of charge that I'm putting down on the surface. And our field strength is proportional to the field line density. Now you'll notice in the formula, our formula for force was K Q1 Q2 over R squared. Our electric field just loses one of those Q's. Both electric field and force are vectors, and so they don't add up numerically. If I have a force of 1 in one direction and a force of 2 in a very different direction, the net force would be on the hypotenuse. Same thing with electric field. They are vectors, and they have to be added geometrically, which is why we like electrical potential, because electrical potential is a scalar. And with a scalar, 1 plus 2 equals 3, no matter what. Our voltage is very similar to our electrical potential. Our electric potential was KQ over R squared. Our voltage is just KQ over R, which means if you know your distance, you can find both of those. They're related to each other. All right, that's going to leave it off for this and finish up our material for our test. So, see you later.